Hey guys, let's go ahead and start reading chapter 6, Sun, Earth, Moon System. So in this first lesson, the key concepts that we are going to be covering are: how does the Earth move? Why is Earth warmer at the equator and cooler at the poles? Why do the seasons change as Earth moves around the sun? So let's go ahead, and today we're going to be reading through this point right here. So go ahead and scroll down and mark right above Earth's rotation. And then let's go ahead and take a look at our science notebook and see that we're going to put our line right there after that first page. That's as far as we're going to get today. Okay? So let's take a look at what we're going to be reading for. We're going to be finding some specific information about the sun that we will come and fill in the chart. All right? So let's go. If you look around you, it does not seem as if Earth is moving. The ground, trees, and buildings do not seem to be moving, but Earth is always in motion. It spins and moves around the sun. Go ahead and highlight that. Earth's motion causes changes on Earth. As Earth spins, day changes to night and back to day again. The seasons change as Earth moves around the sun. Summer turns to winter because Earth's motion changes how much energy from the sun spread out over the Earth's surface. So those are going to be the main concepts for this lesson 1. The sun. The nearest star to Earth is the sun. It is about 150 million kilometers from Earth. The sun is so much larger than Earth. The sun's diameter is more than 100 times greater than Earth's diameter. The sun's mass is more than 300 times greater than Earth's mass. The sun is a giant ball of hot gases. It emits light and energy. Inside the sun, the nuclei of atoms combine to produce huge amounts of energy. This process is called nuclear fusion. Nuclear fusion produces so much energy that the sun's core temperature is more than 15 million degrees Celsius. Now we want to remember that 100 degrees Celsius is boiling, and that's really hot, isn't it? So can you imagine what 15 million degrees Celsius is? Even at the sun's surface, the temperature is about 5,500 degrees Celsius. A small part of sun's energy reaches Earth as light and thermal energy. That's that radiant energy. One thing I want to come out here and write is when it talked about nuclear fusion, that was hydrogen, which is a capital H, and helium, which is a capital H, lowercase e. So it's when they combine, when the hydrogen atom and the helium atom combine, that is nuclear fusion, releasing an enormous amount of energy. Okay? All right, so let's go ahead and stop and go over to our notebook and see what we can fill in. So split screen that, please, with our notebook. So information about the sun. So it's about how many kilometers from Earth? It is about 150 million kilometers from Earth. Energy from, so where did it get its energy? Do you remember that hydrogen, helium? Still learning how to do the typing portion a little bit better. So it's from nuclear fusion. So when they join together, let's put that right there, okay? So the core temperature, it is more than, let's bring that over. It's more than 15 million. That's a lot of zeros. 15 million degrees Celsius. And the surface temperature is 55 degrees Celsius. Okay, there we go. I probably could look and find a degree symbol, but all right, so sun's energy reaches Earth as, we know it goes as light and thermal energy, which is, we know that that is heat. Okay. All right. So we can stop there and make sure that we have all of that typed in. Couple of things I want to write in the margin here is that the nuclear fusion, that's the hydrogen, capital H, and helium, capital H, lowercase e, and just for reference, 100 degrees Celsius. That is boiling. So that gives you a really good reference for what 15 million degrees Celsius and 5,500 degrees Celsius would feel like, right? Okay, so now we are going to go back to our notebook and finish this section here. So I see a vocab word, so we're going to go ahead and highlight that. So Earth's orbit, the motion of one object around another, is called revolution. Earth makes one complete revolution around the sun every 365.25 days. So it's that quarter day that every 4 years adds up for that leap year. The path an object follows as it moves around another object is an orbit. Earth orbits the sun in an almost circular path. Almost. Not exactly circular, almost. Earth's orbit is shown below. All right, so we've got a couple of things going on here. We have inertia, which we remember from back in the fall, the inertia, an object in motion stays in motion. An object wants to travel in a straight line. And then we also have a secondary force of gravity. So the gravitational force here, the sun has a gravitational force pulling on Earth, and that's what keeps it in this motion right here. This is because of the gravitational pull. All right, now if we didn't have inertia, we would just be pulled into that sun. So inertia keeps us wanting to move into a straight line, but at the same time we're being pulled towards the sun. So it keeps us in orbit. So Earth's motion without the sun's gravitational pull, like you see here, we would fling way off into space if we did not have that pull of the sun, the gravitational pull of the sun. So then there are a couple of times in our year when we are, like every 6 months, when we're farthest from the sun. So 152 million kilometers, and when we're closest to the sun, 147 million kilometers. Isn't that interesting that we are a little teeny bit closer to the sun when it is so cold here, huh? So, okay, so let's read a little bit about this. The sun's gravitational pull. Earth orbits the sun because the sun's gravity pulls on Earth. Let's go ahead and highlight that. The strength of gravity's pull between two objects depends on the mass of the object and the distance between them. An object with more mass has a greater gravitational pull than an object with less mass. Likewise, gravity's pull is greater on objects that are closer together. Earth orbits the sun shown above is like the motion of an object twirled on a string. The string pulls the object and moves it in a circle. If the string breaks, the object flies off in a straight line. The sun's gravity is like the string. Gravity keeps Earth revolving around the sun in a nearly circular orbit. If the pull of gravity between the sun and Earth suddenly stopped, Earth would fly off into space in a straight line. So it is both of these, inertia and gravity, that keep us in motion around the sun. So you will have videos and different things that I'll have in place for you that will explain that. This is not the only time you will hear this conversation about inertia and gravity working together to keep Earth in orbit around the sun. If one of them wasn't there, we would not be orbiting. We would have flown off into space, or we would have crashed into the sun. So let's go ahead and fill in our notebook here. So the definition of revolution. Okay, it is the motion of an object around another object. Okay, revolution. So how long does it take Earth to make one revolution around the sun? So that is 365.25 days. So, and that is 1 year, right? And with that, every 4 years, we have a leap year. And that's going to keep our calendar on track, since it's really 365 and 1 quarter day. So every 4 years, that equals then 1 extra day that we have to account for, okay? So what is the definition of an orbit? Orbit is the path an object takes, okay, an object follows as it moves around another object. So orbit is the path an object follows as it moves around another object. So we're really looking, in this case here, our orbit around the sun, okay? So what are the forces that keep Earth in its orbit around the sun? We know that that is sun's gravity, and inertia. Okay, so with gravity, the sun's gravity, autocorrect, sun's gravity I should say, gravity depends on two things. It is the mass of the object and the distance between them. And so the object that has more mass is going to have more gravitational pull. Objects are closer together, they're going to have stronger gravitational pull. Farther apart, not as strong a gravitational pull. So a couple of things I want us to write here in our margin will be that the elliptical and that is the shape of Earth's orbit. And it is almost, nearly circular. Not quite perfect. Okay, and so you can kind of draw it like this. That is an elliptical orbit, okay? So make sure that you have this filled out. Thank you for being patient with me as I am perfecting my typing on Notability. So one more thing I want to talk to you guys about will be this vocab template. Make sure that you are keeping up with the vocab words. So this is going to be from the book. Okay, get those words from the book and then the book definition. So don't be making that up. And then this is some type of image from Google or a drawing of your own if you enjoy drawing. Now, the image needs to match the meaning of the word. Needs to match science meaning. So, for example, in this first part of the lesson, we had the word orbit. Well, I'm really not looking for the orbit gum, okay? So I have the word revolution. I'm really not looking for something having to do with war, all right? So your images need to match what the science meaning of that word is, and because that's going to help you learn that meaning, okay? Alrighty, so keep working on your vocab. Get at least these words done that came from today's reading, and reach out if you